Welcome back to the AI Academy. In this lecture, we will delve into the main components of natural language processing pipeline. Understanding this pipeline is crucial for transforming raw text into actionable insights using computational methods. We'll cover the following 6 steps in detail, like data collection or acquisition, text cleaning, preprocessing, feature engineering, modeling, evaluation, deployment, and monitoring. These steps are similar to those in other machine learning pipelines but focused more towards text-specific processes. Understanding this pipeline is essential for any NLP practitioner. So, moving ahead to the first part, and that is data collection and acquisition. As we know, the data is the foundation of any NLP system. The quality and quantity of the data you collect can significantly impact the performance of your NLP models. In this section, we'll discuss the various sources of data, methods for acquiring it, and considerations to keep in mind to ensure ethical and high-quality data collection. The data for NLP can be sourced from a variety of places. Broadly, these can be categorized into internal and external sources. The internal sources can be business databases. These databases contain structured data generated from business operations. For example, customer feedback, analyzing customer feedback from surveys, support tickets, or social media interactions can help understand customer sentiment and improve products or services. Emails, analyzing email communications can help in tasks such as spam detection, categorization, and automated responses. And transaction records, text descriptions in transaction records can be used for anomaly detection, trend analysis, and recommendation systems. The internal documents, reports, and communication logs can provide valuable insights. Examples include, analyzing internal policy documents can help ensure compliance and detect discrepancies. Employee handbooks, text analysis on handbooks can improve onboarding processes and ensure clarity in policies. The external sources are those data collected from Internet using the techniques like web scraping. The Internet is a rich source of text data. Web scraping involves extracting text data from websites, forums, and social media platforms. The tools for web scraping are Beautiful Soup, a Python library for parsing HTML and XML documents. Scrappy, an open-source web crawling framework for Python. Selenium, a tool for automating web browsers, often used for scraping dynamic content. The use cases of web scraping can be e-commerce reviews, which involve scraping customer reviews from e-commerce sites to analyze sentiment and identify trends. Or the using social media for analyzing posts and comments from social media platforms to gauge public opinion and track discussions. The public datasets, as numerous organizations and academic institutions provide precompiled text datasets that are freely available for research and development. The Common Crawl, a repository of web crawl data that can be used for a variety of NLP tasks. Another use case can be Wikipedia dumps, full text of Wikipedia articles, useful for training language models and other NLP tasks. Even NLTK and Hugging Face datasets provide access to a variety of text corpora for different NLP tasks. When collecting data, it's essential to consider several factors to ensure that the data is usable and legally compliant. So let us first discuss about ethical and legal considerations such as privacy laws, which ensure compliance with data protection laws such as GDPR, General Data Protection Regulation, in Europe, and CCPA, California Consumer Privacy Act, in the United States. Always obtain explicit consent from users when collecting personal data. Anonymize any personal identifiable information, PII, to protect user privacy. Adhere to the terms of service of the websites and platforms from which data is collected. Check and respect the robots.txt file of websites, which specifies the rules for web crawlers. Next is about ensuring data quality, that the data collected is relevant to the NLP task at hand. Irrelevant data can introduce noise and reduce model performance. Also, ensure that the data covers all necessary aspects of the task. For example, if training a sentiment analysis model, ensure the dataset includes a wide range of sentiments. Verify the accuracy of the data. Inaccurate data can lead to misleading insights and poor model performance. Ensure consistency in data format and content. Consistent data helps in building more robust and reliable models. Ensuring that you have high-quality, relevant, and ethically sourced data is crucial for the success of any NLP project. After data collection, the text cleaning is a critical step in the NLP pipeline which prepares raw text for further processing. The goal is to remove non-textual elements and irrelevant information, ensuring the text is in a consistent and structured form. This step helps in making the text more understandable for machines and improves the performance of NLP models. Let us first discuss the importance of text cleaning. Some of them are like, cleaning text reduces noise, which can interfere with the analysis and modeling process. Ensuring a consistent format across the text data makes it easier to analyze and process. Clean text leads to better feature extraction and model performance. Some of the common text cleaning tasks are like removing HTML tags from the web scraped data often contains HTML tags. Removing these tags helps in focusing on the textual content. Next would be normalizing case, where we will be converting all text to lowercase, ensures that words like apple with capital A and apple with lowercase a are treated the same. Similarly, numbers can be handled in different ways depending on the context. They can be removed, replaced with a token, or left as is. For example, scenario replacing all numbers with genum token to standardize numerical representations. The stop words are common words that usually do not carry any significant meaning and can also be removed to reduce noise. Example scenario, removing words like and, the, and, is, to focus on more meaningful words. The other additional text cleaning tasks are like expanding contractions into their full forms. It helps in maintaining consistency and improving the clarity of the text. For example, expanding I'm to expanded I am and it's to expanded form it is. Removing accented characters and ensure that words are represented uniformly. For example, scenario, converting cafe to standardize character representation. Removing special characters and digits can be removed if they do not add value to the analysis. For example, removing characters like asterisk, and digits from text data. And also ensuring that the text does not have unnecessary whitespace helps in maintaining a clean and uniform format. For example, removing leading, trailing, and excessive in-between spaces in the text. Few of the examples you can see below. The tools and libraries used for text cleaning are Beautiful Soup used for parsing HTML and XML documents. And the NLTK library provides utilities for removing stop words and other text processing tasks. And the regular expressions is useful for pattern matching and text manipulation. Moving ahead to preprocessing, it is a crucial step in the NLP pipeline that involves transforming clean text into a structured form that can be easily analyzed and used for building machine learning models. The goal is to convert the raw text into a format that models can understand and learn from. The importance of preprocessing are structuring, which converts unstructured text into a structured format. The uniformity, which ensures consistency across the text data, which helps in better analysis and model training. And the efficiency, which reduces the complexity of text data, making it easier and faster to process. The key preprocessing techniques are tokenization. So, tokenization is the process of splitting text into smaller units, typically words or sentences. This step is fundamental for further analysis and processing. The tokenization is further divided into two parts. The word tokenization, which splits a sentence into individual words. For example, this is an example sentence, becomes this is an example sentence. And the sentence tokenization, which splits a paragraph into individual sentences. For example, the scenario, this is the first sentence. And this is the second sentence. Becomes like, this is the first sentence, this is the second sentence. Further, the sentence segmentation involves splitting a text into sentences. This is particularly useful for tasks where sentence-level analysis is important, such as translation or sentiment analysis. For example, if we are required to perform segmenting a paragraph of customer feedback into individual sentences for more detailed analysis. The next step is stemming and lemmatization to reduce words to their base or root form, which helps in normalizing the text and reducing the dimensionality of the data. So, the stemming removes prefixes and suffixes to get the root form of a word, for example scenario, running, runs, and ran all become run. And the lemmatization considers the context and converts words to their base form using a vocabulary and morphological analysis. For example, better becomes good and running becomes run. Moving to part of speech, which is about tagging parts of speech to each word, such as nouns, verbs, adjectives, etc. This helps in understanding the grammatical structure of the text and is useful for various NLP tasks like named entity recognition and syntactic parsing. For example, the quick brown fox jumps over the lazy dog becomes the DT, quick, JJ, brown, JJ, fox, NN, jumps, VBZ, over, IN, the DT, lazy, JJ, dog, NN. The named entity recognition identifies and classifies entities in the text into predefined categories such as names of persons, organizations, locations, expressions of times, quantities, monetary values, and percentages. For example, in the sentence, Apple is looking at buying UK startup for $1 billion, NR would identify Apple as an organization, UK as a location, and $1 billion as a monetary value. The tools and libraries used for text preprocessing are NLTK, the Natural Language Toolkit. It provides a wide range of preprocessing tools including tokenization, stemming, lemmatization, and POS tagging. The SPACY, an industrial-strength NLP library with efficient implementations for tokenization, POS tagging, and NR. And the Stanford NLP, a comprehensive suite of NLP tools including tokenization, POS tagging, and parsing. Next, we will look into the feature engineering. So the feature engineering is the process of transforming raw data into meaningful features that better represent the underlying problem to predictive models, leading to improved model accuracy. In NLP, feature engineering involves converting text data into numerical formats that can be fed into machine learning algorithms. The importance of feature engineering are representation where we convert the text data into a format that machine learning models can understand. Next is improved performance, where the properly engineered features can significantly enhance the performance of models. And the dimensionality reduction helps in reducing the number of features while retaining essential information, which can lead to more efficient models. The common techniques for feature engineering are bag of words, BAW. It is a model of simplest and most commonly used methods for text representation. It converts text into a set of word counts, ignoring grammar and word order but preserving multiplicity. Where each document is represented as a vector, and each dimension corresponds to a unique word in the corpus. The value of each dimension is the count of word in the document. For example, imagine we have 3 short documents. This is the first document, this document is the second document, and this is the third one. We want to convert these text documents into numerical vectors that our machine learning models can work with. One simple way to do this is by using a method called bag of words. The idea here is to create a list of all unique words from all the documents, and then for each document, we count how many times each word from the vocabulary appears. So, the vocabulary in this case will be: this is the first document, second and third one. So, for document 1, we count the words as: this, 1. Is, 1. The, 1. First, 1. Document, 1. Second, 0. And, 0. third, 0. And 1, 0. So, the vector for the first document is 1 1 1 1 1 0 0 0 0. In this vector, each position corresponds to a word in our vocabulary. The numbers represent the count of each word in the respective document. This simple representation allows us to use numerical data for various machine learning algorithms, enabling us to analyze and process the text data effectively. This is a basic example of how the bag of words model works. While it's simple and easy to implement, it has some limitations, such as ignoring the order of words and potentially creating very large and sparse vectors for large vocabularies. More advanced techniques like TF-IDF and word embeddings can address some of these limitations. Next, we will discuss about the TF-IDF. The full form of SAME is Term Frequency Inverse Document Frequency Technique. The TF-IDF is a statistical measure that evaluates the importance of a word in a document relative to a collection of documents. It adjusts the frequency of words by how often they appear across multiple documents, emphasizing unique words in each document. Let's understand this by breaking it down into two parts: term frequency, TF, and inverse document frequency, IDF. The term frequency measures how frequently a term appears in a document. It's a simple count of the number of times a word appears in a document. The more frequently a word appears, the higher its TF value. For example, if the word cat appears 3 times in a document with 100 words, the term frequency, TF, for cat is 3 divided by 100 is equal to 0.03. Similarly, inverse document frequency, IDF, measures how important a word is by considering how common or rare it is across all documents in the corpus. If a word appears in many documents, its IDF value decreases. This helps in downweighting common words that appear frequently across documents, like the, is, and emphasizing words that are more unique to specific documents. For example, if the word cat appears in 10 out of 1,000 documents. To calculate its inverse document frequency, or IDF, you take the logarithm of the ratio of the total number of documents to the number of documents that contain the specific word. For example, if the word cat appears in 10 out of 1,000 documents, then IDF equals the log of the total number of documents divided by the number of documents containing the word. So, in this case, you take the log of 1,000 divided by 10, which simplifies to the log of 100. This equals approximately 2. TF-IDF helps in identifying words that are important to a particular document while downplaying words that are common across all documents. This is particularly useful in information retrieval and text mining tasks, such as search engines and document classification. If a word appears more frequently in a document, its TF value increases, leading to a higher TF-IDF score. However, if this word is common across many documents, its IDF value decreases, reducing its overall TF-IDF score. This helps in filtering out common words and focusing on unique terms. Next, we will talk about word embeddings. They are dense vector representations of words that capture semantic meaning and relationships between words. In the world of NLP, we often use something called word embeddings to represent words. These embeddings are like continuous vectors placed in a lower dimensional space. What this means is that each word is turned into a list of numbers, and these lists, or vectors, are designed in such a way that words with similar meanings end up close to each other in this space. For example, the words king and queen would have vectors that are very close to each other because they share a lot of semantic similarities, like being royalty. One popular method to create these word vectors is called word2vec. It uses two main approaches: the skip-gram model. This model predicts the surrounding context words given a target word. For instance, if the target word is cat in the sentence, "the cat sat on the mat," the model tries to predict the sat on and the as the context words. And the continuous bag of words, CBOW, this model does the reverse. It predicts the target word based on the context words. Using the same example, it would take the sat, on, and the to predict the target word, cat. Another approach is glove. Glove works a bit differently. It looks at the entire corpus of text and calculates how often words appear together, their co-occurrence. It then uses this information to create vectors that capture the overall relationships between words. Example scenario. Imagine you have a document and you want to turn it into a numerical form that a machine learning model can understand. You can use a pre-trained Word2Vec model to get the vector representations of each word in the document. Then, you can average or sum these vectors to get a single vector that represents the entire document. This way, your document can be compared with other documents based on their content. Pros. These methods capture the semantic relationships between words very well. This means that the vectors for words with similar meanings end up close to each other. The resulting vectors are dense, meaning they are compact and efficient. You can use pre-trained models, which saves a lot of time and computational resources. Cons. Training these models from scratch requires significant computational resources, which can be expensive and time-consuming. Sometimes, pre-trained models might not fit your specific task perfectly, so you might need to fine-tune them, which also requires additional resources and expertise. In summary, word embeddings like Word2Vec and Glove are powerful tools in NLP that help us represent words and documents in a way that captures their meanings and relationships. This makes it easier for machine learning models to work with text data and understand its nuances. Let us now talk about the advanced feature engineering techniques. So the first one is n-grams. Imagine you're reading a sentence and you want to capture the context of each word more accurately. Instead of looking at individual words in isolation, you look at groups of words that appear next to each other. These groups of words are called n-grams. The concept is that the unigrams are just single words. For example, if you have the sentence "this is a sentence," the unigrams are "this is a" and "sentence." Each word is treated separately. The bigrams are the pairs of consecutive words. For the same sentence "this is a sentence," the bigrams are "this is a," and "a sentence." You're looking at word pairs to get a sense of the immediate context around each word. And the trigrams are the triplets of consecutive words. In the sentence "this is a sentence," the trigrams would be "this is a" and "is a sentence." You're capturing even more context by looking at three-word sequences. For example, let's say you're analyzing a document and you decide to use bigrams. By looking at word pairs, you can capture more meaningful patterns. For example, in a text about cooking, the bigram olive oil gives you more specific information than just olive or oil on their own. This helps improve the text representation by considering the local context around each word. If we talk about the pros and cons of using n-grams, then the pros are that by considering adjacent word sequences, n-grams provide a better understanding of the text's local context. This is especially useful for phrases and expressions that carry specific meanings. And also improves representation as compared to single words, unigrams. N-grams can improve the representation of the text by capturing more detailed patterns and relationships between words. The cons are as you increase the value of n, like going from unigrams to bigrams to trigrams, the number of possible n-grams grows rapidly. This can lead to a very large and complex feature space. And with a larger feature space, many of the n-grams may only appear a few times or not at all in your dataset. This sparsity can make it harder to build effective models, as there are lots of features with little data to support them. N-grams are a powerful tool in NLP for capturing the local context of words. By considering sequences of words, they provide a richer representation of the text. However, they also come with challenges, such as increased complexity and potential sparsity. Despite these challenges, n-grams are widely used because they help improve the understanding and analysis of text data. Let's now talk about topic modeling. This is a really cool technique that helps us discover the hidden topics within a collection of documents. Think of it as a way to automatically organize a large set of texts by identifying common themes or topics that run through them. One of the most popular methods for topic modeling is called latent Dirichlet allocation, or LDA for short. To explain how it works, so the LDA assumes that each document in your collection is made up of a mixture of a few different topics. For example, a news article might be about politics, but it might also touch on economics and technology. And it also assumes that each word in the document is related to one of these topics. So, in our news article, words like government and election might be attributed to the politics topic, while words like stock market might be attributed to the economics topic. For example, imagine you have a large collection of news articles and you want to understand what they're generally about without having to read each one. You can use LDA to analyze these articles and identify the main topics. For instance, after running LDA, you might find that there are common themes like politics, sports, and technology across the articles. Each article can then be represented as a mixture of these themes. An article could be 70% about politics, 20% about sports, and 10% about technology. Let's talk about pros and cons of it. The pros are that, one of the biggest advantages of LDA is that it's unsupervised. This means you don't need to manually label your data before running the algorithm. It can automatically discover the topics for you. And it also provides valuable insights into the underlying structure of your data. You can see how different topics are distributed across your documents and how they relate to each other. And on the downside, LDA can be computationally intensive, especially with large datasets. It requires significant processing power and time. And the algorithm also requires fine-tuning of parameters like the number of topics. Choosing the right number of topics can be tricky and might require some experimentation. So, topic modeling with LDA is like having a magic tool that reads through your documents and tells you what they're about. It breaks down each document into a mix of topics, helping you understand the main themes without diving into every single text. While it's powerful and insightful, it does need some computational muscle and careful tuning to get the best results. The tools and libraries used for feature engineering are scikit-learn, as it provides implementations for bag of words, TF-IDF, and other feature extraction methods. Next is Generative, a popular library for topic modeling and word embeddings. And the Spacie is efficient for generating word embeddings and other NLP tasks. And the NLTK, which offers basic tools for text processing and feature extraction. The topic we will discuss now is modeling, so with the numerical data ready from the feature engineering step, the next stage is modeling. This involves applying machine learning or deep learning algorithms to learn patterns from the data. The choice of model depends on the specific NLP task, such as classification, regression, or clustering. The importance of modeling is that the models learn patterns and relationships in the data, enabling predictions and insights. And different models are suited for different NLP tasks, such as sentiment analysis, text classification, and language translation. And the choice and tuning of models significantly impact the accuracy and efficiency of the NLP system. Let us now talk about the common models in NLP. Let's dive into Naive Bayes, a straightforward yet powerful tool in the world of machine learning. It's a probabilistic classifier that's especially handy for text classification tasks, like deciding whether an email is spam or not. The term naive Bayes comes from Bayes' theorem, a fundamental concept in probability theory. Here's the naive part. This classifier assumes that the presence of any particular feature, like a word in an email, is independent of the presence of any other feature. In other words, it treats each word as if it has nothing to do with any other word in the email, which is a pretty strong and often unrealistic assumption. But despite this simplification, it works surprisingly well in many cases. For example, imagine you have a bunch of emails, and you want to build a system to automatically sort them into spam and not spam. Naive Bayes can help you do that. It looks at the words in each email and, based on how often these words appear in spam versus not spam emails, it calculates the probability that a new email belongs to one of these categories. For instance, if the word free appears a lot in spam emails and rarely in non-spam emails, seeing the word free in a new email increases the probability that it's spam. The pros of this model are that Naive Bayes is easy to understand and implement. It's quick to train and predict, making it great for real-time applications. Even with a small amount of training data, Naive Bayes can perform surprisingly well. Given its simplicity, it's particularly effective for text classification tasks where you have lots of features, words, and need a quick solution. And the cons are that the biggest drawback is the naive assumption of independence. In reality, words in a document are often related. For example, free and offer might appear together in spam emails. This assumption can sometimes limit the classifier's performance. In a nutshell, Naive Bayes is like a smart, quick decision maker that can help sort your emails into spam and not spam by looking at the words in them. It's simple and fast, making it a great tool for text classification tasks, especially when you need something quick and effective. However, it does make a big assumption that all features are independent, which might not always hold true in real-world scenarios. Despite this, it's a trusty tool in the machine learning toolkit that often punches above its weight. Let's now talk about support vector machines, or SVM for short. These are really powerful tools for classification tasks, and they shine especially when dealing with data in high-dimensional spaces, like text data. At its core, SVM is all about finding the best way to separate your data into different classes. Imagine you have a bunch of points on a graph, and you want to draw a line, or a plane, or a hyperplane in higher dimensions, that separates the points of one class from the points of another class. SVM finds the optimal hyperplane that best separates the classes with the maximum margin. This means it's looking for the line that has the largest distance to the nearest points of each class. This way, it ensures that the separation is as clear as possible. For example, let's say you have a bunch of news articles, and you want to categorize each one into topics like sports, politics, and technology. SVM can help you do that. It takes the words from the articles, turns them into a high-dimensional feature space, and finds the hyperplane that best separates articles from different categories. So, an article full of words like game, team, and score might get classified under sports, while one with election, policy, and government would go under politics. The pros of using this model is that the SVM is really good at handling data where the number of features is large, which is often the case with text data. Think about all the different words in a corpus. And it's robust to overfitting, particularly in high-dimensional space, because it's designed to find the best margin between classes. And the one downside is that SVM can be computationally intensive, especially as the size of your dataset grows. Training the model can take a lot of time and resources, which can be a limitation when dealing with very large datasets. So, the support vector machines are like expert separators. They excel at drawing the best possible line, or hyperplane, to divide your data into different categories. This makes them great for tasks like classifying news articles into topics. They handle high-dimensional spaces well and are resistant to overfitting, making them robust and reliable. However, they do require significant computational power, especially for larger datasets. Despite this, their ability to create clear and effective separations makes them a powerful tool in the classification toolkit. Let's now talk about decision trees and random forests, the two powerful techniques used in machine learning for making predictions. A decision tree is a model that makes decisions by splitting data into branches. Imagine it like a flowchart where each decision leads to a different branch. The concept is that think of a decision tree like an actual tree. At the top, you have a single node, the root, which represents the entire dataset. From there, the tree splits into branches based on different decision rules, like whether a word appears in a text or not. And each split represents a decision point that separates the data into smaller subsets. These decisions continue until the tree reaches the leaves, which represent the final predictions or outcomes. For example, imagine you're doing sentiment analysis on customer reviews. A decision tree could split reviews based on words they contain. For instance, it might first check if the word excellent appears. If it does, the tree might predict a positive sentiment. If not, it might look for another word like bad to decide if the sentiment is negative. Now let's talk about the random forests. They take the concept of decision trees to the next level. Instead of relying on a single tree, they build multiple decision trees and merge their results. The random forests are an ensemble method, meaning they combine the results of multiple models to improve accuracy. Each tree in the forest is built using a random subset of the data and features. And the final prediction is made based on the majority vote of all the individual trees. This approach helps in reducing the chances of overfitting and improves the model's generalization to new data. The pros are that the decision trees are straightforward to understand and interpret. You can easily follow the tree's decisions to see how a prediction was made. And they can handle both numerical and categorical data, making them versatile for various types of tasks. And the random forests are robust to overfitting because they average the results of many trees, each of which might overfit in different ways. And the cons are like the decision trees can overfit the training data if they grow too deep, making them less effective on new data. While random forests improve accuracy, they are less interpretable than single decision trees because they aggregate the results of many trees. In a nutshell, decision trees and random forests are like a team of experts making predictions. A single decision tree is like one expert making a series of decisions to reach a conclusion. It's easy to understand how it makes decisions, but it can sometimes be too specific to the training data. Random forests, on the other hand, combine the wisdom of many experts, multiple decision trees, to make a more balanced and robust prediction. They handle a variety of data types well and are resistant to overfitting, but they can be more complex and harder to interpret. These techniques are great for tasks like sentiment analysis, where you need to classify text data into categories like positive or negative reviews. By using decision trees and random forests, you can build models that not only perform well but also provide insights into how decisions are made. Let us now explore about neural networks. So the neural networks are like the rock stars of the machine learning world. They're incredibly powerful and can handle really complex tasks, especially in natural language processing, NLP, like language translation and text generation. Let's talk about the different types of neural networks used in NLP and how they work. So, the first is recurrent neural networks. RNNs are designed to recognize patterns in sequences of data. Think of text, for instance, where the order of words matters a lot. RNNs have loops in their network structure, which allows them to maintain information over time. This means they can remember what happened in previous steps and use that information to make decisions. For example, imagine you're trying to predict the next word in a sentence. If you have the sentence, "I am learning to," an RNN can use the context from the previous words to predict the next word, which might be code or write. The next one is long short-term memory, LSTM, is a special kind of RNN that can learn long-term dependencies. While standard RNNs can struggle with remembering information from far back in the sequence, LSTMs are designed to handle this better by using special structures called gates to control the flow of information. For example, suppose you're doing sentiment analysis on a long movie review. The sentiment at the end of the review might depend on something mentioned at the beginning. LSTMs can help capture these long-term dependencies and provide a more accurate analysis. And the next one is transformers. The transformers are the latest and greatest in NLP models. Unlike RNNs, they don't process the text sequentially. Instead, They use something called self-attention mechanisms to look at all the words in a sentence simultaneously. This allows them to understand the context of each word in relation to all other words, making them incredibly powerful and efficient. For example, one of the best examples of transformers in action is machine translation. If you're translating a sentence from English to French, transformers can understand the context of the entire sentence at once, producing more accurate and fluent translations. The pros of the neural networks, especially RNNs, LSTMs, and transformers, are that they are excellent at understanding and capturing complex patterns in data. And they achieve state-of-the-art performance on many NLP tasks, from text generation to translation and beyond. The cons are that to perform well, neural networks often need a lot of data. They learn from examples, so the more data you have, the better they can learn. Training these models can require significant computational resources, like powerful GPUs and lots of memory. And setting up and fine-tuning neural networks can be complex. There are many parameters to tweak, and getting the best performance often requires a lot of experimentation. Neural networks, including RNNs, LSTMs, and transformers, are like the heavyweights in the machine learning world. They can tackle really tough problems and deliver impressive results, especially in NLP. RNNs are great for recognizing patterns in sequences, LSTMs handle long-term dependencies well, and transformers use self-attention to process entire sentences at once, making them incredibly powerful. However, they do require a lot of data and computational power, and setting them up can be a bit tricky. But when you get them right, they can do amazing things, like accurately translating languages or generating human-like text. Let's now talk about pre-trained language models like BERT, GPT-3, and Roberta. These models have really changed the game in natural language processing, NLP, by using a clever approach to learning from massive amounts of data. The pre-trained language models are first trained on huge datasets using unsupervised learning. This means they learn patterns, grammar, and even some facts about the world just by reading lots and lots of text. After this pre-training phase, the models can be fine-tuned on smaller, task-specific datasets. This fine-tuning helps them excel at specific tasks like answering questions, classifying text, or analyzing sentiment. For example, imagine you're building a system to answer customer questions. Instead of training a model from scratch, which would require a massive amount of data and time, you can use a pre-trained model like BERT. You take BERT, which already understands a lot about language from its pre-training, and fine-tune it on your specific dataset of customer questions and answers. This way, the model quickly adapts to your specific needs and performs really well. The pros of using pre-trained model is that, the pre-trained models deliver top-notch performance on a wide range of NLP tasks. They set new benchmarks for accuracy and efficiency. Because they've already learned a lot from the pre-training phase, these models need less data for fine-tuning. This makes it easier to achieve good results even if you don't have a massive labeled dataset. The knowledge these models gain during pre-training can be transferred across different tasks. This means you can use the same model for various NLP applications, from text classification to sentiment analysis, with just a bit of task-specific fine-tuning. And the cons are that the initial pre-training phase demands a lot of computational power and time. Companies often use powerful GPUs or TPUs and large clusters to handle this. These models can be very large, requiring substantial memory and storage. This can make them challenging to deploy, especially on devices with limited resources. In a nutshell, pre-trained language models like BERT, GPT-3, and Roberta have revolutionized NLP by allowing us to leverage extensive pre-training on massive datasets. They can then be fine-tuned for specific tasks, making them highly versatile and powerful. They offer state-of-the-art performance and reduce the need for large labeled datasets, but they do require significant computational resources for pre-training and can be quite large. Despite these challenges, their ability to understand and process language at a high level makes them invaluable tools in the NLP toolbox. Let's now break down the process of model training and tuning. It's like teaching a child how to solve a puzzle. You guide them through learning, check their progress, and make adjustments to help them get better. Let's walk through this process step by step. So, for training process, first things first, we need to divide our data into 3 parts. The training set, this is the bulk of your data. It's what you'll use to teach the model. Validation set, it is smaller portion of the data is used to fine-tune the model. Think of it as a practice exam before the final test. And the test set, this is another small portion of the data, kept separate from the others, used to evaluate how well the model performs on completely unseen data. Next, we move on to training the model. This is where the real learning happens. You use the training set to teach the model by showing it examples and adjusting it to minimize errors. This is done using optimization algorithms like gradient descent, which helps the model learn from its mistakes and improve over time. Once the model is trained, it's time for some fine-tuning. You use the validation set to tweak the model's hyperparameters, which are the settings you configure before training. The goal here is to prevent overfitting, which is when the model learns the training data too well and fails to generalize to new data. By fine-tuning on the validation set, you ensure the model performs well on data it hasn't seen before. Finally, you evaluate the model's performance using the test set. This is like the final exam. The test set helps you see how well the model performs in real-world scenarios, ensuring it's ready for deployment. If it does well on the test set, you can be more confident it will work well in practical applications. To sum it up, training and tuning a model involves several key steps. For example, divide your dataset into training, validation, and test sets. Use the training set to teach the model by minimizing errors. Tune the model using the validation set to prevent overfitting and improve generalization. Evaluate the final model's performance on the test set to ensure it's ready for real-world use. By following these steps, you can develop a robust model that not only learns well from your data but also performs effectively when faced with new, unseen data. Let's now talk about hyperparameter tuning. So when you're training a machine learning model, there are certain parameters called hyperparameters that you set before the training starts. These aren't learned from the data but are crucial in defining how the training process will unfold. Tuning these hyperparameters can have a huge impact on how well your model performs. Think of hyperparameters as the settings on an oven. If you're baking a cake, you need to set the right temperature and time. Too high or too low, and your cake won't turn out right. Similarly, setting the right hyperparameters is essential for getting your model to perform well. The methods of hyperparameter tuning are like grid search, so the grid search is like testing every possible setting on your oven to find the perfect temperature and time for your cake. You manually specify a range of possible values for each hyperparameter. Then, grid search systematically tries every combination of these values to see which combination works best. For example, if you're tuning a model and you have 2 hyperparameters, say learning rate and batch size, you might specify 3 possible values for each. Grid search will then try all 9 possible combinations, 3 learning rates x 3 batch sizes. The next method is random search. In the random search is like testing a random selection of oven settings rather than every single possible combination. So, in this method, instead of trying every possible combination, you sample hyperparameters from specified distributions. This means you randomly pick a set of values and see how well they perform. For example, using the same 2 hyperparameters, learning rate and batch size, instead of trying all combinations, random search might randomly pick a few combinations to test. It's less exhaustive but often finds good solutions more quickly than grid search. And the third method is Bayesian optimization. The Bayesian optimization is a bit more sophisticated. It's like having a smart assistant who learns from each baking attempt and suggests better settings for the oven based on past results. The Bayesian optimization uses Bayesian techniques to model the performance of hyperparameters based on past trials. It predicts which combination of hyperparameters will perform best and tests those, refining its model as it goes. For example, starting with a few random combinations of hyperparameters, Bayesian optimization analyzes the results, predicts better settings, and focuses on testing those. Over time, it improves on the optimal set of hyperparameters more efficiently than grid search or random search. Hyperparameter tuning is all about finding the best settings for your model before you start training. By carefully tuning your hyperparameters, you can significantly boost your model's performance. It's like fine-tuning an oven to bake the perfect cake. The right settings make all the difference. So, once you've trained your model and tuned its hyperparameters, the next step is to evaluate how well it performs. This means checking to see if it meets your goals and performs well on your data. We do this by using various metrics, which are like report cards that tell us how well the model is doing. The types of metrics are classification metrics. These metrics are useful when your task is to classify data into categories, like spam versus not spam. You use classification metrics. Some of the key ones are like accuracy. This is the simplest metric, telling you what percentage of your predictions are correct. If your model is right 90 times out of 100, it has 90% accuracy. Next is precision, which measures how many of the predicted positive cases are actually positive. If your model says 10 emails are spam and 8 really are, your precision is 80%. The next one is recall. It measures how many of the actual positive cases your model correctly identifies. If there are 10 spam emails and your model catches 8 of them, your recall is 80%. Another one is F1 score. This is the harmonic mean of precision and recall, giving you a single number that balances both. It's useful when you need a balance between precision and recall. And another one is ROCUC, receiver operating characteristic, area under the curve. It is a metric that shows how well your model distinguishes between classes. Higher values mean better performance. The next are regression metrics, and it is used when your task is to predict a continuous value, like the price of a house. You use regression metrics. The main ones are mean squared error, MSE. This measures the average squared difference between the predicted and actual values. Lower values are better. Mean absolute error, MAE. This measures the average absolute difference between the predicted and actual values. It's more interpretable since it's in the same units as the data. And the R-squared. This tells you how well your model explains the variance in the data. A value closer to 1 means your model explains most of the variance. Another type of metrics are task-specific metrics, as some tasks require specialized metrics to better evaluate model performance. Some of them are BLU score. This is used for machine translation and measures how close the model's output is to a set of reference translations. Higher scores indicate better translations. And the Rouge score. This is used for summarization tasks and measures the overlap between the model-generated summary and reference summaries. It evaluates both precision and recall of the overlap. Evaluating your model is like giving it a thorough checkup to see how well it's performing. So for the classification metrics, use accuracy, precision, recall, F1 score, and ROCUC for tasks where you classify data into categories. For the regression metrics, use MSE, MAE, and R-squared for tasks where you predict continuous values. And use task-specific metrics. Use specialized metrics like BLU for translation and Rouge for summarization to get a more accurate picture of your model's performance. By using these metrics, you can make sure your model is not just good in theory but also performs well in practice, meeting the specific needs of your project. Let's break down the examples of these models. For text classification, imagine you get a lot of emails every day, and you want to automatically sort them into spam and not spam. That's what text classification does. For this task, you might use a naive Bayes model or a support vector machine, SVM. These models are great at looking at the words in the email and figuring out whether it's junk or something you actually want to read. With a good model in place, your inbox gets cleaned up efficiently. All the spam emails get filtered out automatically, so you only see the emails that matter to you. For sentiment analysis, let's say you run an online store and you want to know how customers feel about your products. Sentiment analysis helps you determine whether customer reviews are positive, negative, or neutral. For this, you might use an LSTM, long short-term memory, model or a pre-trained BERT model. These models can understand the context of the reviews and determine the sentiment behind them. By identifying whether reviews are positive or negative, you can get a better understanding of customer satisfaction. This helps you improve your products and services based on feedback. Another use case is language translation. Suppose you need to translate a document from English to French. Language translation models can help you do that automatically. A transformer model, like the one used by Google Translate, is perfect for this task. It looks at the entire sentence and translates it into another language while maintaining the correct grammar and meaning. You get accurate translations, making it easier to communicate across different languages. This is especially useful for businesses operating in multiple countries or for anyone learning a new language. And in the last take example of named entity recognition, NR, so let's say you have a lot of text data and you need to extract specific information like names, dates, or locations. Named entity recognition helps you identify and classify these entities in the text. You could use a CRF, conditional random fields, model or a pre-trained BERT model for this task. These models can spot and categorize entities accurately. NR extracts useful information from your text data, making it easier to organize and retrieve specific details. This is particularly useful for tasks like information retrieval and data analysis. These examples show how powerful and versatile NLP models can be, helping you handle various tasks efficiently and effectively. The tools and libraries used for modeling are: scikit-learn, a comprehensive library for basic machine learning models including naive Bayes, SVM, and decision trees. TensorFlow and Keras are powerful libraries for building and training deep learning models. PyTorch is a popular framework for building deep learning models, especially favored for research and development. And Hugging Face Transformers provides easy access to pre-trained models like BERT, GPT-3, and more. Let us now discuss about the cross-validation. The cross-validation is like giving your model a thorough workout to make sure it performs well not just on the data it was trained on, but also on new, unseen data. It's a technique used to evaluate how well your model generalizes to different sets of data. So, how it works: the idea is that instead of just splitting your dataset into two parts, one for training and one for testing, you split it into multiple parts, called folds. You then train and test the model multiple times, each time using a different part of the data as the test set and the remaining parts as the training set. This way, you get a more reliable assessment of your model's performance. There are two ways to perform the cross-validation. One is k-fold cross-validation. In this, imagine you have a dataset and you divide it into equally sized parts, or folds. Let's say you choose k equals 5. You then train and test your model 5 times. Each time, you use a different fold as the test set and the remaining 4 folds as the training set. For example, if you have a dataset of 1000 entries, with 5-fold cross-validation, each fold would have 200 entries. In the first round, you might use the first 200 entries for testing and the remaining 800 for training. In the second round, you use the next 200 entries for testing and so on until every fold has been used as a test set. This way you end up with 5 different performance scores, one for each round. By averaging these scores, you get a more robust estimate of how well your model is likely to perform on new data. And the second one is stratified cross-validation. So the stratified cross-validation takes it a step further by ensuring that each fold has the same proportion of classes as the original dataset. This is particularly useful if you have an imbalanced dataset where some classes are much more common than others. For example, suppose you're working with a dataset where 90% of the entries are Class A and 10% are Class B. With stratified cross-validation, each fold will also maintain this 90-10 split, ensuring that the class distribution is consistent across all folds. This approach ensures that the evaluation is fair and that the model's performance is tested in a way that accurately reflects the class distribution in the real world. The cross-validation, and particularly k-fold cross-validation and stratified cross-validation, is like putting your model through a series of mini-exams to make sure it's really ready for the big test. By repeatedly training and testing the model on different parts of the data, you get a more reliable measure of its performance. And by using stratified cross-validation, you ensure that each mini-exam reflects the actual distribution of your data, giving you a fair and accurate assessment. This helps you build a model that performs well not just on your training data, but also on new, unseen data. Let's now move to deployment. So the deployment involves making the trained model available for use in a production environment where it can process real-world data and provide predictions or insights. This stage requires careful planning and execution to ensure the model operates efficiently and effectively. Let's dive into the details of deployment strategies for machine learning models. Deploying a machine learning model means putting it into a production environment where it can start making predictions on real-world data. There are two main strategies for deploying models: batch processing and real-time processing. Each has its own use cases and benefits. The batch processing involves handling data in large chunks at scheduled intervals rather than continuously. This approach is suitable for tasks where immediate responses are not necessary. In this, data is collected and stored over a certain period. And at the scheduled times, like nightly, weekly, the model processes this accumulated data in one go. The results are then stored and used as needed. For example, for the customer review sentiment analysis, suppose you run an online store and customers leave reviews about their purchases. So, instead of analyzing each review as it comes in, you collect all the reviews over a week. And at the end of the week, you run a sentiment analysis model to determine the overall customer sentiment. The results can help you understand customer satisfaction and identify any recurring issues. The pros of such deployment are that by processing data in large batches, you can optimize the use of computational resources. And is easier to manage large volumes of data as processing is done periodically. And the cons are that there is a delay between when data is collected and when insights are generated. Not suitable for tasks requiring immediate feedback. The second strategy is real-time processing. So in the real-time processing handles the data as it comes in, providing immediate predictions. This approach is crucial for applications that require instant responses. The model is integrated into a system that continuously feeds it new data. As soon as new data arrives, the model processes it and generates a prediction on the spot. The prediction is immediately available for use. For example, in the case of real-time language translation, imagine a chat application that supports multiple languages. When a user sends a message in English, the application immediately translates it into French for a French-speaking recipient. This is possible because a language translation model processes each message as it's sent, providing instant translations. The pros of such models are that it provides instant predictions, making it ideal for applications that require real-time decision-making. And enhances user experience by delivering prompt responses. And the cons are that it requires continuous computational resources, which can be costly. And handling high volumes of data in real time can be challenging, requiring robust infrastructure. The choice between batch processing and real-time processing depends on the specific requirements of your application. For example, choose batch processing if your task can tolerate some delay in generating predictions. It's ideal for applications like periodic reporting, data aggregation, and historical analysis. Choose real-time processing if you need immediate predictions and responses. It's essential for applications like live chatbots, fraud detection systems, and personalized recommendations. Next, let's dive into the details of setting up APIs for deploying machine learning models. So the first step will be of setting up the API, or Application Programming Interface. It is a set of rules that allows different software applications to communicate with each other. When you set up an API for your machine learning model, it enables other applications to send data to your model and receive predictions in return. This is a crucial step for integrating your model into production systems where it can be accessed and used by various clients. There are two common types of APIs used for deploying models: RESTful APIs and gRPC. Let's explore each one. The RESTful APIs are based on representational state transfer (REST) principles and are widely used for web-based applications. They allow communication over HTTP, the same protocol used for web browsers to interact with web servers. The key APIs are like HTTP method. The RESTful APIs use standard HTTP methods like GET, POST, PUT, and DELETE to perform actions. GET API retrieves data from the server. The POST API sends data to the server to create a new resource. And the PUT API updates an existing resource on the server. The DELETE API removes a resource from the server. Each API call is independent, and the server does not store any information about the client between requests. And also, each resource, like a user or a data entry, is identified by a unique URL. The basic steps to set up a RESTful API are: choosing a framework. The popular frameworks for setting up RESTful APIs are Flask, Django, with Django REST Framework, and Fast API in Python. The next step is to create endpoints for your API that define the URL structure and the associated HTTP methods. For example, an endpoint for making predictions could be predict, which accepts POST requests. The next step is to write functions to handle incoming requests, process the data, call your model for predictions, and send back the response. And in the last, deploy your API on a server using a hosting service like AWS, Google Cloud, or Heroku. For example, in the case of Sentiment Analysis API, the endpoint will be predict, and the HTTP method will be POST. The request will a JSON object containing the required text for the sentiment analysis, and in return the response will be again a JSON object with the respective sentiment prediction. The next type of API is gRPC. It is a high-performance, open-source framework developed by Google. It uses HTTP/2 for transport, protocol buffers, protobuf, for serialization, and provides features like load balancing, authentication, and more. The key APIs are HTTP/2, which supports multiplexing multiple requests over a single connection, improving performance. The protobuf API uses protocol buffers, a language-neutral and platform-neutral interface definition language for serializing structured data. The streaming API supports bidirectional streaming, allowing for real-time data exchange between client and server. The strongly typed feature enforces strict type checking for reducing errors. The basic steps to set up a gRPC API are: first, define the service, where you need to write a .proto file that defines the service and the methods it offers, along with the message types. For example, a service for sentiment analysis might have a method predict sentiment that takes a text request and returns a sentiment response. The next step is to generate code, for which you can use the protocol buffers compiler to generate client and server code from the .proto file. And write the server-side logic to handle the methods defined in the service. And finally, deploy the gRPC server on a suitable hosting platform. For example, scenario: in the case of sentiment analysis gRPC service, the service definition will be like service sentiment analysis RPC predict sentiment text request return sentiment response, and the request will be a protobuf message containing the text. And the response will be a protobuf message with the sentiment prediction. Both approaches have their own strengths and are suitable for different types of applications. By setting up an API, you make your model accessible, enabling it to provide predictions and insights in a production environment. Let's now talk about some popular tools you can use for deploying your machine learning models. These tools make the whole process smoother and more efficient, allowing you to deploy, manage, and scale your models effectively. At the first, deploying a machine learning model involves making it accessible for real-world use, whether that is through a web service, an application, or some other means. Some of the popular tools that can help you with this are like, Docker. It is a platform that allows you to containerize your applications. Think of it like packaging your model and all its dependencies into a neat, portable box. This makes it much easier to deploy the model consistently across different environments. You create a Docker image that includes everything your model needs to run, like libraries, code, and even the operating system. When you deploy this image, Docker ensures it runs the same way on any machine. For example, if you've trained a model on your laptop, you can package it into a Docker container and be confident that it will work exactly the same way on a server in the cloud. The next tool is Kubernetes. Kubernetes is an open-source system for automating the deployment, scaling, and management of containerized applications. It works really well with Docker. So, the Kubernetes orchestrates your Docker containers, ensuring they run smoothly. It handles tasks like load balancing, scaling up or down based on demand, and recovering from failures. For example, if you deploy your model in a Docker container and suddenly get a spike in users, Kubernetes can automatically create more containers to handle the load and ensure your application remains responsive. Another set of tools are Flask and Django. They are popular Python web frameworks that you can use to set up APIs for serving your models. So, the Flask is a lightweight and flexible micro-framework that's easy to set up and allows you to build simple APIs quickly. For example, you can write a few lines of code to create an endpoint where users can send data and get predictions from your model. And the Django is a full-featured framework and a robust that comes with a lot of built-in features for web development. For example, if you're building a more complex application that needs not only model predictions but also a user interface, authentication, and more, Django provides all the tools you need. Also, there are cloud-based platforms available, like AWS SageMaker, Google AI Platform, and Azure Machine Learning. All of them provide comprehensive tools for deploying and managing machine learning models in the cloud. The AWS SageMaker is an end-to-end solution which allows you to build, train, and deploy models all in one place. For example, you can train your model using SageMaker's infrastructure, deploy it with just a few clicks, and then manage it through a web interface. And the Google AI platform integrates well with other Google Cloud services, making it easy to deploy models and use them in a variety of applications. After training your model, you can deploy it as an API that scales automatically and integrates with tools like Google Cloud Functions. And the Azure Machine Learning provides a suite of tools for model deployment, including automated machine learning, DevOps for machine learning, and more. You can use Azure's tools to automate the deployment process, ensuring your model is always up to date and running smoothly. Deploying a machine learning model can be complex, but these tools make it much easier. Like Docker, packages your model into a container, ensuring it runs consistently across different environments. Kubernetes manages and scales your Docker containers automatically, making sure your application can handle varying loads. Flask and Django allow you to set up APIs to serve your model, whether you need a simple endpoint or a full-fledged web application. AWS SageMaker, Google AI Platform and Azure Machine Learning are cloud platforms that offer end-to-end solutions for building, training, deploying, and managing models. Using these tools, you can deploy your models efficiently, manage them effectively, and scale them as needed, ensuring they perform well in real-world applications. Okay, let us now delve into the details of monitoring deployed machine learning models. Once you've deployed your machine learning model, the work doesn't stop there. Continuous monitoring is crucial to ensure your model stays effective and performs well over time. Monitoring involves regularly checking the model's performance, spotting any issues early, and making updates as necessary. Let's break down its key components. The performance monitoring is about keeping an eye on how well your model is doing its job. This involves tracking various metrics to ensure the model remains accurate and efficient. Here are some key aspects to focus on: prediction accuracy, track metrics such as accuracy, precision, recall, F1 score, and ROC, AUC. The proportion of correct predictions made by the model. Monitor the proportion of true positive predictions among all positive predictions. The proportion of true positive predictions among all actual positives. And the harmonic mean of precision and recall, providing a single metric that balances both. The area under the receiver operating characteristic curve, indicating the model's ability to distinguish between classes. Monitoring these metrics helps you understand if the model's predictions are still reliable. A drop in any of these metrics might indicate that the model's performance is degrading, which could happen due to changes in the input data or other external factors. Also monitor latency, for example, measure the time it takes for the model to provide a prediction after receiving a request. Monitor the total time taken from receiving the input to delivering the prediction. The time taken by the model itself to process the input and generate a prediction. Ensuring that the model meets required performance standards for latency is crucial, especially for real-time applications. High latency can negatively impact user experience and may indicate inefficiencies in the model or system. For example, imagine you've deployed a sentiment analysis model that processes customer reviews in real time. Here's how you might monitor its performance. You will regularly check the precision, recall, and F1 score of the model to ensure it's correctly identifying positive and negative sentiments. And set up alerts to notify you if any of these metrics drop below a certain threshold, indicating a potential problem. Ensure that this response time stays within acceptable limits, such as under 1 second for real-time analysis. There are various tools available for monitoring your deployed models effectively. Some of them are Prometheus, an open-source monitoring system that collects metrics from various sources, stores them, and allows you to query and visualize them. Grafana, a popular open-source platform for monitoring and observability, which can be integrated with Prometheus to create interactive dashboards. ELK Stack, containing Elasticsearch, Logstash, Kibana, a powerful suite of tools for searching, analyzing, and visualizing log data in real time. And also, AWS CloudWatch, Azure Monitor, Google Cloud Monitoring for cloud-native monitoring solutions that provide comprehensive tools for tracking the performance of applications and infrastructure. Let's now break down the concept of model drift. So, the model drift is like when your car's alignment gets off over time. Even though it worked perfectly when you first got it, gradually, it starts to veer to one side because the road conditions have changed, or parts have worn out. Similarly, your machine learning model might start to perform poorly over time because the data it's being fed has changed in some way. There are two main types of model drift. First one is concept drift, which happens when the relationship between the input data and the target variable changes. It's like the rules of the game have shifted. For example, imagine you have a sentiment analysis model that predicts whether customer reviews are positive or negative. Over time, if customer behavior changes, maybe they start using different words or phrases to express their feelings. In that case, the model might not be as accurate because it was trained on older behavior patterns. The second one is data drift, which occurs when the distribution of the input data itself changes. It's as if the ingredients you're using in a recipe have altered. For example, suppose you have a text classification model that categorizes social media posts. If new slang or seasonal language starts trending, the words the model encounters could be quite different from what it was trained on. For instance, during the holiday season, phrases like holiday sale or New Year might become more common, impacting the model's performance. To keep your model performing well, you need to detect and address model drift. So, to handle such cases, perform regular retraining. It is like taking your car for a regular tune-up. By periodically retraining your model with new data, you ensure it stays up to date with the latest trends and patterns. Every so often, you gather the latest data, retrain your model using this updated dataset, and then redeploy it. This helps the model adapt to new behaviors and data distributions. Configure automated alerts which act like the warning lights on your car's dashboard, alerting you when something's wrong. Set up a system to monitor your model's performance metrics continuously. If there's a significant drop in accuracy, precision, recall, or any other relevant metric, the system sends an alert. This immediate notification allows you to investigate and take action before the performance issues become critical. By keeping an eye on model drift and taking proactive measures, you can ensure your machine learning models continue to perform effectively over time. Let's now break down error analysis so, when your model makes mistakes, it's not the end of the world. In fact, these errors can be incredibly informative. By analyzing the errors, you can understand where and why your model is going wrong and then make improvements. The two key techniques for error analysis. First one is confusion matrix. A confusion matrix is like a report card for your classification model. It shows you exactly how many times your model got things right and where it went wrong. The confusion matrix has four main components, and they are true positives. It is the number of times the model correctly predicted the positive class. Another is true negatives, the number of times the model correctly predicted the negative class. And false positives are the number of times the model incorrectly predicted the positive class, also known as type 1 error. And false negatives are the number of times the model incorrectly predicted the negative class, also known as type 2 error. For example, suppose you have a spam detection model. The confusion matrix would show that how many actual spam emails were correctly identified as spam. How many legitimate emails were correctly identified as not spam. How many legitimate emails were incorrectly flagged as spam. And how many spam emails were missed and not flagged. It gives you a clear picture of your model's performance. By seeing where the errors are occurring, you can focus on improving those specific areas. Let us now discuss about error distribution. So, analyzing the error distribution involves looking at the types and frequencies of errors your model makes. This helps you spot patterns and understand common pitfalls. After identifying the errors, categorize them to see if there are any common themes. Look at the frequency of each type of error to understand which ones are most problematic. For example, continuing with the spam detection example, you might find that your model frequently misclassifies emails with certain keywords or from specific senders. You might also discover that the model struggles more with certain types of spam, like phishing emails, compared to others. It helps you identify patterns in the errors, which can point to specific areas where your model needs improvement. Understanding the distribution of errors can guide you in collecting more targeted training data or adjusting your model to handle these tricky cases better. Let's now break down A/B testing. It is like a head-to-head competition between two versions of your model to see which one performs better. Think of it as a way to compare the old way of doing things, Model A, with a new approach you're testing out, Model B. You take two versions of your model, one that's currently in use, Model A, and a new version you've developed, Model B. You split your users or data into two groups. One group gets predictions from Model A and the other from Model B. By comparing the performance of these two models on the same task, you can see which one is better. It helps you make informed, data-driven decisions about whether to update your model. You get a clear, side-by-side comparison of performance metrics, so you can confidently choose the best model. Let's go through some real-world scenarios to understand how deployment and monitoring work. You've built a sentiment analysis model that determines whether customer reviews are positive, negative, or neutral. This model is deployed using a RESTful API, which means it's accessible over the web. Your company's review system sends each new review to this API, which then returns the sentiment score. Regularly track the sentiment scores the model assigns to reviews. Pay attention to any drops in performance, which might happen if the language customers use changes over time. For example, new slang or expressions might not be well understood by the model. If you notice the model isn't performing as well, you can retrain it with more recent reviews to keep it accurate. Suppose you've integrated a spam detection model into your company's email system to filter out unwanted messages. This model works in real time, analyzing each incoming email and deciding if it's spam or not. Keep track of precision and recall metrics. Precision tells you how many of the emails marked as spam actually are spam, and recall tells you how many spam emails the model is catching. Monitor for any increase in false positives, legitimate emails marked as spam, or false negatives, spam emails not caught. Periodically retrain the model with new data to adapt to evolving spam tactics and patterns. Similarly, for the language translation, you've developed a real-time language translation model that's deployed using gRPC for high performance. This model is used in applications like chat services where instant translation is necessary. Regularly evaluate the translation quality using BLU scores, which measure how close the model's translations are to human translations. If the quality drops, it might be due to new slang or idiomatic expressions that the model hasn't seen before. Update the model with new training data as needed to maintain high translation quality. By understanding these concepts and examples, you can effectively deploy, monitor, and improve your machine learning models, ensuring they perform well in real-world applications. With this, we wrap up our discussion on deploying, monitoring, and maintaining your machine learning models. We've covered essential strategies for ensuring your models remain effective and reliable over time, including handling model drift, performing error analysis, and using tools like Docker, Kubernetes, and cloud-based platforms for deployment. In our next lecture, we're going to dive into a powerful tool for natural language processing, the NLTK, Natural Language Toolkit, library. We'll explore how to use NLTK for tasks like text preprocessing, tokenization, and more. Make sure to join us for an in-depth look at this versatile library that can help you handle a wide range of NLP tasks. We hope you found this introduction to NLP informative and engaging. If you liked learning from this lecture, please give it a thumbs up and subscribe to our channel. Your support keeps us motivated for creating more valuable content for you. Thank you for watching, and see you in the next lecture.